Yo, what is up, guys? Welcome back. Episode, I think 118 or something. Yeah, 118 today. Let's check out. It is a Golding today, so let's take a look at the sound, shall we? It's been a long day, man. Played a hell of a sport this morning, so I'm pretty exhausted, but let's take a look.
Golding, 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 Golding.
Golding, 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 Golding. Golding, 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 Golding.
Golding, 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 Golding.
Golding, Golding, Golding. Sounds like it's singing Golding, Golding, Golding. Alright, we had a nice and easy sound today. Let's take a look at our problem of the day. Yeah. Substitutes denoted have a length of k, the following holes. I'm a little confused with the description. Yesterday, what description ever take? I'm not even gonna bother with this question. I mean, this description is just horrible. I don't even want to think about it. Let's take a look at a 2DP problem. Then we'll take a look at another advanced graph problem. Let's do coin change 2. Okay, you're given an array of coins representing the coins of different denominations and an integer amount representing total amount of money. Return the number of combinations that make up that amount. If that amount of money cannot be made up by any combination of the coins, return 0. You may assume that you have an infinite number of each coin. The answer is guaranteed to fit into a signed 32-bit integer. Okay. We did do coin change 1. I think that was a 1DP problem, I think. Yeah. So I'm thinking either we take, or we skip, or we take, or we skip, or we take, or we skip. That's what I'm kind of thinking here. So I'm thinking some sort of like backtracking solution, while keeping track of the count. That's kind of my intuition. So obviously we need probably like an I. We need our, that's our profit, right? I guess if I is greater than or equal to the length of coins, I guess we're not technically looking. Well, not technically looking at I. We'd probably be looking at, okay, we check, well, if profit is greater than or equal to amount, I guess if profit is equal to amount, right? This would be our base case. If our profit is equal to the amount, then we can simply return. But I'm thinking, we need some sort of count. Count is equal to 0. Let's have like a non-local count in here. Again, we're doing the base case solution here. Now we do count plus or equal to 1, right? And we return. We check, well, if the profit is greater than amount, then I think we would just return. Otherwise, I guess this is the recursive part. We need to make some choices, right? So either we go with count and we go, okay, well, and we go backtrack, we stay at I, and we stay at I. Jeez, what was wrong with my shirt? We stay at I, or we we can stay at I and not do anything. Okay, profit plus coins I, or we can backtrack I plus 1 profit plus coins I. Right, these are our two choices. Okay, let's call our backtracking function. We start at 0 with our count. Sorry, with our profit is 0. And we would return our count. List index is out of range. I guess we'd have to do that too. I guess that would maybe be another base case if I is greater than or equal to the length of coins, then I guess what we'd probably return too. Or else, like, it's not gonna work, right? Expected 4, we got 6, we got 0. 2, we got we were close. I think our thinking is right, but maybe we messed up something. 518 coin change 2. What's wrong with my brute force solution? Brute force solution is almost correct in its structure, but has a subtle bug in the recursion logic that causes You're counting permutations instead of combinations, in some cases because of this line. So apparently the only thing that I got wrong here is that I need to keep the same profit. Really? You can reuse each coin as it may sometimes is needed, so you state index I while taking a coin. To avoid permutations, only move I plus 1 when skipping the coin. Brute force will hit the TL in large outputs. Wow. Nearly got it. Was unlucky. Sorry, let's submit. Let's get that TLE error just to make sure. Then we want to add some Mimo. Some Mimo. Time not exceeded. Okay, so what we want to do here is now we want to create a Mimo, right? We would probably get rid of this non-local count. Okay. Probably want to use where we're at with the I and the profit. So if profit I, make this DP, profit I in DP, then we want to return DP profit I, right? Profit is equal to amount. We want to return 1, right? Get rid of that. Profit is, I'm not sure. Amount or I. Select coins. We return 0. Okay, we get rid of that. Rid of that base case. Probably want to move this. Right, down here. Okay. Then you do take is equal to backtrack. Skip is equal to this, and then we probably want to do take and a skip, but then we probably want to do like some sort of max, I think. Let's do dp ij is equal to the sum of take and skip. Would it be the sum? I guess that works. And we want to return dp Definitely should be the other way around. I didn't really think about that. I think that was just side profit. Whoops. This just has to be take plus skip. There we go. If I profit NDP, Alright, I'll be back in a second. I gotta go to the bathroom really quick and then we'll keep going. So, 1 second. Alright, I'm back. Yeah, I'm back. Sorry. Okay, let's take a look at cheapest flights with case stops. Rock your body. Rock that body. Rock that body. Cheapest flights. Cheapest flights with case stops. Got a 40% acceptance rate. Jeez. From to price. In case there's a flight from city from to with cost price. You're also given 3 integers, source, des, and k. Return the cheapest price from source to des with at most k stops. If there is no such route, return -1. So we're given a source. From 0, we have to get to 3 to find the cheapest length. I think this is going to be the same algorithm as the other day, I think. Prims, I think? I believe... is 787 the cheapest flights within K stops. A Prims algorithm question. Oh, this is a directed graph. Okay. best solved using a variant of Dijkstra's algorithm or BFS with a Q. Okay. I believe we should probably build an adjacency list first. So let's do that. Def adjacency list. We pass in. I'm just gonna call it edges. Right. Okay, so we go. Okay, so for I in for edge in edges. Our first edge is the source, so we just want to make the just want to make the destination and the weight. So I believe we'd probably go something like this. A B C is equal to edge. So if A not in graph, then graph A is equal to dot pend VC. Let's just do, okay. Or I guess we can just graph A dot append and BC return graph. Then we call the function adj list. We pass in our flights. Let's print our graph. Zero, 1, 2. Where the hell is 3? we don't use the default dick. Maybe we just go, okay, well, for I in range length flights. No. I think it would work without the 3, I think. Okay, so now we have our adjacency list. I believe we would need a visited set. Visited is equal to set. Okay, we would need a min heap, right? We will need to append the weight first. So 0. We want to base it off the weight, right? And min heaps only go off the first value is what they base it off. So we would go 0, and our starting node is 0, right? And we go while min heap. Okay, we want to pop, so let's do weight node is equal to heap q dot heap pop min heap fuck, what is this value here? I have to look at the heap q documentation, dude. Oh my god, heap q documentation. Heap q dot heap pop heap. Okay. How do we import heap q low key? How to import heap q Python. Jeez, dude. Come on, rock that body, rock that body, rock that body. Come on, rock that body, rock that body. From collections. Oh, do we not need to? Okay, yeah. And we would check, okay, well, if node in visited, then we want to continue, right? We don't want to use it. Otherwise, what will be the next part? Probably add it to the visited set, right? Visited.add node. Then we probably want to do the BFS part where we would probably loop through each of our things, right? So for dest in what is it called? Graph node. Destined graph node, we want to do, okay, well, we need this documentation because now we want to heap push. So we do heap q dot heap push. We want to push to our min heap. And what was the other parameter? We want to, what item we want to push? We want to push destination. Oh, we want to push the weight. So we'd probably want to do I guess these are lists technically, so this needs to be a tuple, not a list. BC. W plus W2 dash 2. Here's, yeah, W plus W. Okay, so we didn't do that. Yeah, W2 and dest. In graph node, we do W plus W2, passing our destination. We need to check here. Well, so if node is equal to the, what is K? With at most K stops. Well, this changes it a little bit with the K. I didn't read the problem properly, but if we have a K, then probably a min heap isn't probably good here. We probably want to just switch this to a BFS. Right. We don't really need the shortest path. I guess we can track that in a different way. Oh, shit, dude. Oh, I'm cramping. Oh, shit. Oh. Oh. God damn it, dude. Oh, man. Okay, so min heap dot append. I guess we were gonna need some sort of like K here, right? I think we can do it with K. Okay. So then we push W node and we push our K, right? Node and visited, we continue, we visit or add node. So then we would do, okay, well, if I guess if the node is equal to the destination, I don't think this is gonna work. If node is equal to the destination, right? Then we just want to check the distance, right? So we would need to do, I guess we probably need some sort of like res or something, right? Okay, let's say res is equal to let's make it float infinity, right? So we check, okay, well, if the node is equal to the destination, then we take the min. Is it raining outside? It's storming. Then we take the min. Sorry, we would take the res is equal to min. And we would take the min of res as well as I guess, our current weight, right? Otherwise, if our K is equal to 0, then I think we just want to skip this iteration, right? I guess we would just want to skip the iteration. Okay, right? And then we would simply just want to return our res, right? Return res if res does not equal float inf, else we want to return -1, right? Do the BFS part. K is equal to 0, we continue. If node is equal to destination, res is equal to min, visit is add. Then we would... I don't think this is going to work, but like... Let's just run it, see what we get. Collection start... Oh, whoops. It feels like it's like 7 o'clock at night right now. None of values from my pack. Expected 3, got 2. Why are we... Oh, wait, no. Okay, stops. You're actually stored edges as desk cost. Have I? Bro. Oh, yeah, I have. This needs to be CB. Whoops. Using visited blindly can prune valid cheaper paths with fewer stops. Missing K when pushing to the heap. Whoops, K -1. Got that. Okay. Incorrect use of visited set. We want to use visited blindly. Unlike Dash's classic armor, next phase guaranteed to be better. Here, the path cost can decrease with more stops, so you should track visited by both node and stops. Apparently I should keep this. VC. They don't even use a visited set. Would we even need a visited set? Because we have a directed graph, so I don't even think maybe we'd need a visited set. I'll put 500, expected 200. Oh geez, yeah, I'm starting from 0, but we want to start from source. SRC. Node is hard coded as 0. Is it too slow? Memory limit exceeded. Why am I getting a memory limit exceeded, dude? Like, what? Let's get rid of print. Let's get rid of this. I don't think we need this anymore. For this, we would just return -1. Getting a TLE, dude. What the hell? Getting a TLE? You're not pruning worse paths. Even if a node has been visited before with more remaining stops or lower costs, your algorithm revisits it needlessly. To fix this, we add a minimization fee. Okay. visited is equal to set. Oh, they use a dictionary for the set instead. Keys equal to node, values equal to max stops left seen with cheaper costs. Okay, if node and visited node is greater than or equal to stops, we would just continue. Visited node is equal to stops. Visited node, sorry, is equal to. Okay. There we go. Okay. That was a good problem. Shit. Oh. Let's jump into like a random problem. So why not? Jeez, man. My back. Dude, it's killing me. I don't know. I want to jump in some random problems. Let's just search some problems, fill some problems, and pick one. That's the last problem to do today. Take a look at a medium problem. Difficulty is medium. Yeah, that's cool. At a distance, I saw this one somewhere. Let's do like an easier problem, maybe. Binary search tree iterated in? What is this? Implement the BST iterated class. Okay, let's take a look at this. The BST iterated class represents iterator of the in-order traversal of a binary tree. So in order would be root. Sorry, no, left, right, left, root, right. Traversal. Left, root, right. Left, root, and right. Yeah, okay. So pre-order would then be root, left, right. Root, left, right, yeah. And then post-order would be... Shit, man, I don't even know. Is it right? Where's I think it's right, root, left? Left, right, root. Okay, left, right, root. Okay. Anyway. The BST iterator class represents an iterator over the in-order traversal. Okay, of a binary search tree, BST iterator tree initialize an object of the BST iterator class. The root of the BST is given as part of the constructor. The pointer should be initialized a non-existent number smaller than any element in the BST. Boolean has next returns true if there exists a number in the traversal to the right of the pointer, otherwise returns false. Okay. Int next moves the pointer to the right and then returns the number at the pointer. Okay. So I think it's self.root has next. So let's do, okay, well, if self.root.right, we return true, otherwise we return false. Okay. Move self.root. I just don't know how to do this class. Initialize an object BST iterator class. The root of the BST is given as part of the initializer. The pointer should be initialized to a non-existent number. What the hell does that mean, dude? Like, I have literally no idea. Like, bro, who writes these? Chill, bro. I don't know what this means, dude. 173 binary search tree iterator. Oh, wait, really? Oh, dude, my back. Dude, my back hurts so bad. I'm gonna cramp again. seemed a lot more simple. Okay, so they're saying that here, well, actually we need to do self.stack is equal to this. And then we need some sort of like go left function. It doesn't really say that in this. Like, I'm a little confused. BSC iterator. I think this is kind of a stupid question, to be honest. Yeah, I'm gonna leave this question. I think this is a stupid question. Like, so confusing. Count primes. Give an integer and return the number of prime numbers that are strictly less than n. Seems like a good one. How to calculate a prime number. I know a prime number is a number that cannot be, I think it's like times together, like, or something like that. Divided by whole numbers from 2 up to its square root. Dude, that doesn't really help. A prime number must be greater than 1. Check for divisibility by 2. If the number is even, it's divisible by 2 and therefore not a prime, except for the number 2 itself. Test divisibility by prime numbers up to its square root. Find the square root of the number. Divide the number by each prime number less than or equal to the square root. 2, 3, 5, 7, 9. We're going to be doing like a prime number lesson, dude. Oh, is not efficient. I was literally thinking about that. Check all the integers in the range 1 to n minus 1 is not efficient. Think about a better approach. What would be a more efficient way? Is this an easy problem? What even is this, bro? Like, what is sieve of... What is this crap? Like... Big Mac the mathematician. I'm just gonna do this problem because I don't want to look for another one. This is gonna be our last problem for the day. How to solve I bet you Leetcode has a video on this too, bro, because I'm... No, he doesn't. Okay, so if n is less than or equal to 2, we would return 0, right? Because anything less than 2, we know is not a prime, right? Because 2 is our first prime. 2 is first prime, okay? So they're saying that we create an array. So let's say primes is equal to true times length of n, right? Actually, we don't need to take the length of n, we just need n, right? So then we make prime 0 is equal to false. Primes 1 is equal to false, right? Because we know 0 is false for sure, and we always know 1 is false, right? Thus, I believe we probably loop through for I in range length range n in range starting from 2. Okay, we got, it says here int n times 0 y plus 1. Outer loop. Iterate of all numbers starting from 2 up and including the integer square of n. Man, this is a little confusing, dude. Count primes 2 at 4.
Welcome to Maze Leetcode Challenge. Today's problem is count primes. Count the number of prime numbers less than a non-negative number n. So if we're given the number 10, we're going to return 4 because there's 4 prime numbers less than 10. 2, 3, 5, and 7. So I believe it's inclusive. And they give you a ton of hints here. It's a classic problem, and I think it's good to kind of go through the basic intuition. The first thing that we need to understand is that 0 and 1 are not primes. And that should be obvious, but it's good to remember that. Now, normally when you solve this problem, say you were doing this in an interview, you could probably just move from the numbers like 4, 1 to n, and for each one of these, like check to see in range of like whatever this number up here, if it's none of these are divisible for that number within this range. So say that we had the number 5, we could check to see, all right, is it divisible from any number between 2, 3, 4? If it's divisible by any of these numbers, exclusive, that means it's not prime. Now it should only be divisible by its number itself, so 5 and 1, right? But that would end up becoming like an n squared solution. It's pretty inefficient. It might be perfectly accepted in an interview, but we can do better. And I actually read about this recently. There's an algorithm known as the sieve of Eratosthenes, okay? And here's the basic idea. What we'll do is build an array from 0 to all the way to n, the number that we're trying to check for. And what we'll do is first mark all these index numbers as true. Now what we'll do is build up from the bottom up. We'll start with number 2 because 0 and 1 are not primes. And for every number that we can add 2 to, other than the number itself,
I just didn't really know how to calculate. We'll go back to that video. We'll see if this accepts. It probably won't, but so let's do def is prime, right? We're gonna probably pass in like a num, right? Otherwise down here we want to make count is equal to 0. Okay. For num in range starting at 2 going to n, if is prime num, okay, then we're going to increase our count by 1 and then simply return our count afterwards, right? Now our is prime function, we'll check, okay, well if num is less than 2, okay, then we would simply return false, right? Otherwise, we would loop through for I in range starting from 2, right? Yeah. We would, this does a square root, int num times by 0.5 plus 1. Then we would check, well, if num percent I is equal to 0, so if it's divisible by that number, we would return false. Otherwise, it's a prime number, we would return true. This is not an if, sorry, this is a for. I didn't know to find the prime you would use the square root. I don't think this submits that.
Itself 2 is a prime because we're building this top up. We'll just mark that as prime immediately. But every number that we add 2 to, like 4, 6, 8, 10, all of these are not going to be prime numbers. So we have to mark all of those as false. Now once we get to the end, we'll start at 3. Now 3 has not been marked as false, so we'll keep that. And then we'll move for all the multiples of 3, 3, 6, 9. If any of those are not marked as false, we mark those as false all the way up to the final range. But we continue this algorithm until we've marked every single one of our numbers. And the key thing is when we check the index number here, if it's already marked as false, then we can skip it, because that should mean that everything before that was already marked false. Okay, so here's what we'll do. The first thing we'll check is if n is equal to 0 or n is equal to 1, we can immediately return 0. Next, we're going to create a array of primes, and the index number is going to represent the number. Now I know 0 and 1 are already should be marked false, so we'll do that as well. We'll say, okay, mark these all as 1 for now, making that a true. And then we'll say, all right, primes 0, make that equal to 0, and primes 1, also make that equal to 0. Okay, so now we need some sort of iterator, and we start at number 2. So while, let's see, I is less than n, what do we want to do? Well, now we're going to have this nested for loop, but we're going to check all the multiples, right? And what I'll do here is, if the primes of I, if this is marked as true right now, that means we want to do our for loop. So we'll say, okay, this is marked as true, but everything else, every multiple after that, we're going to mark as false. So what we'll do is create a temp, and we'll say, all right, let's mark this temp here equal to the I, and to the temp we'll say plus or equal I, and all the primes of temp, now we're going to make that equal to false. And we have to do this in a while loop. Let's say while temp is less than n. We're going to mark every single one of these like this. Once we're out of this, we're going to increase our I by 1. Now at the very end, we should have an array of all the index numbers either marked as true or false. So we're just going to return the sum of these primes right here. So let me make sure I got this right. Here we'll test out number 10. Ooh, okay, times temp. Okay, so I think what I have to do is put it at the end and increase it just one time right before this while loop. Alright, so right here you can see 2, 3, 5, 7 are marked as prime numbers, and that's true, right? So this should work for any number. Let's go ahead and submit this. And there we go, accepted. So time complexity wise, it's going to be n log n. Although technically, I think if you want to get really technical, it's log or n log of n.
If n is less than 2, we can instantly just return 0, right? Otherwise, we want to make a primes, and we can make it 1 times n. Primes of 0 is equal to 1, or is equal to 0. And primes of 1 is equal to 0, right? Understand that part, right? So now we want to loop through. Well, okay. What does he do? He does while I is less than n, temp is equal to I, if primes I, so if it's for I in range 2 until n. 2 till n, right? That looks weird. I don't know why. We make our temp is equal to I. If primes I don't understand this part. Like, if primes I, temp plus or equal to 1. plus or equal to I. While temp is less than n. Primes temp is equal to 0. Temp plus or equal to I. I plus or equal to 1. I don't understand this part here. I don't get. And then we want to return the sum of primes. Primes I. Temp is equal to I. Right, so we're at 3. If primes I, temp plus or equal to I. So we add 3. While temp is less than n, primes temp is equal to 0. Temp plus or equal to I. I don't believe we need this. I don't think. Okay, I understand. I was getting confused with the plus or equal to I. I was like, how is this doing the multiplication? But then I realized that it's just adding 3, not actually timesing. That was so stupid of me, but alright, anyway. We're going to call the video there. I appreciate you guys watching. I will see you tomorrow.